everyone. Today at Newcom, we are very excited and very proud to present our first ever neuromorphic platform, Ada. So Ada is a Turing-complete neuromorphic processor and computational framework. Unlike traditional neuromorphic solutions, which mostly focus on AI acceleration, Ada is designed as a general-purpose neuromorphic processor. So it leverages brain-inspired technology from neuromorphic computations to deliver sparse and low-power products to combat real-world problems like latency, power, and memory. So without further ado, let's quickly go through the agenda for today. So first, we're going to start off with our motivations behind developing Ada. Then we're going to go as a refresher into the neuromorphic concepts. Then we move on to look into some general-purpose neuromorphic frameworks. And then we deep dive into the actual hardware of our Ada chip. And then we finish off strong with our use cases and our future for Ada. So as we all know, the world is producing more than enough data for today, be it from video signals, audio signals, or biosignals. All of this huge amount of data is flowing through edge devices. And so basically, the embedded architectures of today are really struggling to keep up. So there's a huge growing mismatch between the demands for modern algorithms of today and the hardware architecture solutions that we have. So basically, mostly for edge devices, they combat two problems, be it sensor to inference bottlenecks, like for example in case of pre-processing data and denoising, which suffer from software and hardware constraints, or to data security, like for example in case of implantable medical devices. Some people, they have to turn off encryptions just to save on power, which can leave sensitive data exposed. And this is not ideal case. So to combat these solutions, so basically the manufacturers of today, they have to choose between really inflexible but high-performance ASIC solutions, or flexible but underpowered microcontrollers, or really bulky FPGAs. So each come with their own set of drawbacks, be it high power, low flexibility, or the need for specialized expertise. So with all these in mind, we developed Ada, and Francesco, our CFO, our CSO will introduce how Ada will fit as a solution in all of these.
Thank you, Abir. So we think at Newcom, we think that the solution lies in moving to a novel computing paradigm to solve the existing tech limits. So that means venturing into unconventional computing, which is the discipline that studies how processing of data is done in natural systems in order to hopefully reverse engineer this principle and come with new devices, algorithms, and ways of processing information that takes inspiration from this system. So among the most recent or famous ones, we have optical computing and quantum computing, but then we also have neuromorphic computing, which is what we're looking at Newcom and what we're building our tech on. And neuromorphic computing is an abstraction of how the information is processed in real biological neurons. So as you can see here, neurons operate with voltage traces, and neuromorphic computing takes these voltage traces, simplifies them into a Boolean abstraction called spikes, and carries out computation by propagating these spikes in neural networks. So here, very simplified mechanism of how this works in a spiking neuron. You have inputs coming to the neuron over time, so these series of spikes reaches the neuron, and then there's a threshold comparison, so if enough spikes come into the neuron, then the neuron fires out other spikes, and these form the output to following neurons in the network. So this is very attractive because it creates sparsity in the network, so it allows to save a lot of energy by not crunching numbers, but processing these Boolean events over time. And we're already seeing that in neuromorphic, existing neuromorphic devices. So there's already proof that this type of technology can scale beyond the digital circuit limits, even though it's still kind of an early tech. So the design are still based on stable digital platforms, but we expect these power savings to be even bigger as we move to analog or mixed signal substrates, because this will create even more sparsity, or it will allow to have more sophisticated processing of this information. However, even if we scale the tech, we still believe there's more to take advantage out of neuromorphic by moving the spike-based computation beyond just inference core as there is now, and essentially cram more of the edge AI pipeline into this spike-based framework. Because we think that this could allow to have less reliance on CPU, so less data movement or less CPU leverage for processing the actual data. And we think this could lead also to increase end-to-end efficiency, meaning in the whole edge AI pipeline from sensor to inference core, this could allow to have more savings throughout the way. So we started by also asking ourselves, what can be done now, and what are the computation that could benefit most from these substrates? And to answer the question, there's few general purpose frameworks that are out there, let's say, and we're just going to present a few of these. The first one that we started looking into is called Neuroengineering Framework, NEF, which is a very powerful framework. It allows to model dynamical systems out of rate-based neurons, but this creates, so it's very good to simulate state space problems, but being rate-based neurons, this creates a lot of spikes. So it's a very dense spiking activity. This is not really what we want for sparsity. Also, there's noise reading, so there's some overhead when cleaning the signal out of this population activity. The second framework, which is called Fugu, it's a very modular framework. It's incredibly flexible, so it allows to model a lot of different algorithms, but this flexibility comes at the cost of the user. So algorithms have to be, let's say, manually defined, or they are built by stacking these components together, but in a way that is not really standardized. It's a lot of, let's say, empirical way of building these algorithms through the SDK. And finally, we looked into STIC, the spike time interval computational kernel. So in this framework, as the name suggests, values are encoded in time between consecutive spikes. So the interval between two consecutive spikes is what encodes the numbers. And this allows to have, again, extreme flexibility. It's a Turing-complete framework, but the problem relies on the fact that because of this encoding strategy, the higher the resolution, the longer the time needed to faithfully encode numbers in these spike intervals. Dima is going to actually show how we solve this, but this is one of the drawbacks of the vanilla implementation of STIC that can create a big latency. Also, there's limited real-world validation because this has been proposed, let's say, almost 10 years ago as a journal article, but then it hasn't been shown a lot of application in the real world. So these are, let's say, all the framework that we explore with some of the drawbacks, but we liked STIC so much that we're sticking with it. No pun intended. So as I mentioned, it's a time-based framework, so it allows to convert from a continuous domain to a time interval domain and vice versa. And the way it works is ultra sparse. That means that not only there's 2 spikes needed per encoding, but also the networks that are built with STIC have very low synaptic fan-in and fan-out. So that means that the spikes traveling through the networks are very sparse. There's not a lot of spike traveling simultaneously in the networks. And also, another great point of it is its Turing completeness because of its modularity. Because there's few computational primitives that are defined as very small networks. We're talking about roughly between 5 and 10 neurons each. And these networks can be stuck together, so they can be composed by encapsulating the primitives into a block in which only the input and output neurons are exposed as interfaces. And by just combining these into a more complex, let's say, modular algorithm, one can replicate any function that he wants. Note that all of these components, they just manipulate the time interval that they receive encoded as 2 spikes. So it's just by manipulating time interval and reading the corresponding interval that is sent as output, we can actually do this computation. So now Dima, our CTO, is going to tell you all about our invention.
Thank you. So here we have ADA, which stands for Asynchronous Data Flow Architecture. And basically what we're trying to do here is take this STIC interval coding framework and apply it to an embedded architecture and a hardware platform, as well as a software environment to deploy this kind of computation that we kind of identified before with data security and the entire sensor to inference pipeline, and basically apply this interval coding framework to allow neuromorphic computation on this embedded hardware platform. So here we have, we're kind of taking advantage of the extensibility that the STIC framework provides, and really trying to implement a hardware architecture that achieves this neuromorphic benefit for a lot of these different classes of computation. So Ada, at its core, is generally it's an engine for executing these interval-coded spiking neural networks. It's fully programmable in the sense that an algorithm that or a spiking neural network representation using this interval coding framework that represents some class of computation can be loaded and dynamically loaded onto this device. And we provide standard interfaces for moving data to and from chip using the encoder logic. And for certain applications, you may want to use a UART or AER for DVS cameras and for both sparse or continuous data flow. We also provide a standard interface for the tile link, which allows us to configure and load the model by a host CPU. And also in terms of the actual neuron core, this fits within a 16,000 LUT FPGA, apart from the actual neuron logic. And this is very small in terms of area, and this is kind of the benefit that we're trying to expose with this neuromorphic framework, that we can actually reduce the amount of computation by using this interval coding architecture. Now, on top of this, a big challenge that we want to address is also the fact that we don't want people to have to develop and implement this interval coded networks and even be too much exposed to this architecture whatsoever. Now, how we kind of address this, we exposed it's what we call Axon SDK, which is it's basically a suite of tools that allows you to take some computational representation in Python, NumPy, or C, and then deploy this through a compiler, and then export a binary file that just represents the actual neural and synaptic connections within the actual Ada device. And this is loaded over a runtime API, which is part of your companion microcontroller. And this kind of allows you to actually make this move an algorithm all the way to our device without actually having to interact with any training or managing the network whatsoever. Now, if you wanted to do that, we also provide a network simulator, which is also open sourced. And this allows extension or implementation of new modular primitives, one of which we'll introduce in a bit, and a hardware emulator, which kind of gives you an idea of what are the resource usage, the timing estimates in terms of latency that you can expect, apart from just deploying it on the device. So one of the good benefits of the encoding and decoding architecture is the ability to kind of scale up the amount of data flow that is being brought from the continuous domain to this interval coded domain. This is just kind of giving an idea of what the encoding architecture looks like on a combinational circuit. Quite simple to implement, highly configurable for different precisions of data types from in a continuous domain moving to the spiking event-based area. Now, one of the issues with this temporal-based processing that we found in the spiking neural network representation that we're using STIC is basically when you're dealing with higher levels of precision, we see that this basically requires a larger window of execution. And what that means is that the amount of neural updates that we need to do scales linearly with the size of the precision. And in terms of our neural core, one kind of idea we had was when an event occurs, we can actually predict in advance the time when this neuron will fire in the future. And what this allows us to do is we don't have to do any neural updates within this entire process. So this actually reduces the amount of computation from scaling linearly to logarithmically, which is a huge benefit in terms of latency and also in terms of just generally performance and area. And in terms of the neural update, the idea here is that the neural update is composed only of add, multiplying, shift, which is very cheap to implement on hardware. So this kind of allows us to create more complex functionality by just using primitive neural updates with simple hardware blocks. Now to get into maybe some more practical use cases, I think we'll start with a simple one. This is a 3-tap finite impulse response filter. We have the encoded interval coming here. It goes through a multiplication block, which is one of the primitives that stick provides. It's multiplied by a constant, and then passes through a synchronizer from the previous xn minus 1 and x of n minus 2, and then synchronized so that these intervals are all synchronized at the same execution window, and then pass through a linear combination block, which implements the function for FIR. This is only 110 neurons, so we can implement this. It kind of just shows how the computational graph looks. This is the output from a logical perspective of what a compiler would generate, and it kind of describes how a fairly complex computation is represented using these stick primitives. Now, one use case that is particularly exciting for us is actually fitting Ada within this entire, with a audio or video or event-based processing stream. And the idea here is that Ada is a programmable processing element that can implement denoising, spatial temporal encoding, and kind of remove the CPU from any kind of pipeline or processing within this entire core data flow. So where a certain routine for maybe tensor formatting that would be done in, for example, TensorFlow or spiking jelly in the case of using spiking neural networks, we can actually apply all of this and basically treat Ada as a hardware accelerated autoencoding layer. And this remains entirely in the event domain within Ada, and we're able to apply, basically hoist the CPU completely out of the execution process. And in terms of latency and memory movement, we significantly reduce the amount of computation that's not being done on accelerated hardware. Now, just as an example of this, we basically applied spatial temporal denoising to the DVS 128 gesture dataset, and we actually found that it significantly reduces the amount of computation using the Ada-based network that applies this function by over 50%. So in terms of the actual data reduction that is actually being used for the model for classification of gestures, we can see that the amount of data that's actually being processed at the end of this pipeline is significantly lower. So we see this as a kind of a nice fit in terms of also applied for audio, video, and this is specifically for the DVS event-based cameras. So this is something that's very interesting for us. Now, going further, we did mention also this data security pipeline, and this is something where we had to spend some time and actually extend this framework even further. And it's, I think, very novel from our end in terms of trying to apply cryptography to a neuromorphic framework. And that's what that took is that we actually had to apply a new modulus primitive, because this is a very important operation or primitive operation within the cryptography domain, where most arithmetic is done with an extension using modulus, so that everything stays within a finite field or finite polynomial ring. And in the case of, for example, a post-quantum cryptography algorithm called Kyber or MLChem, which is a key encapsulation mechanism, we actually see that over 50% of the operations really boil down to actually doing this modulus arithmetic. So we kind of wanted to address this main issue or computational bottleneck with this neuromorphic framework and see if how we can apply a lower power neuromorphic cryptography to an IoT device where post-quantum cryptography and even security in general is already quite a challenge. Can we apply this and apply this computation to the Ada device? Now, in terms of actually implementing this network, it really boils down to something called polynomial multiplication. And really what we're trying to show here is how a higher level network is constructed based on simple primitives that are extended. So you can see the butterfly operations. These are basically implementing on elements within a polynomial so that we can do something called the number theoretic transform. And this basically actually was did the polynomial multiplication, same how it would be done on software, and we benchmarked it compared to MCU benchmarks from NIST, which is a standardization body, and we saw that we actually achieved 5 times better power efficiency, and the energy delay product being at 2.5 times better. Latency is slightly higher because of some digital scheduling logic, which we expect to optimize in future device revisions. But in general, we see this as a promising first development and deployment of and realization of the Ada product. Now, in terms of summary and future use cases, kind of where we want to go with this is we want to harden the actual device on a mixed signal domain to really squeeze more opportunity for power efficiency, and really explore some further use cases and hard on these use cases. So some of the ones that we see a good fit for are audio, video, and potentially cryptography as well. And with this, we've also exposed our Axon SDK, which is our software environment, and we expose this. We have publicly released this for anyone to try this network out, and we encourage anyone with use cases in mind, with questions, to feel free to reach out, and we'll be happy to explore them.